Alright, we're going to start our fourth unit today, and we're going to look at how we can use derivatives and everything we've learned so far to help us draw better graphs. So our first lesson today, we're just going to focus on graphing using the x and y intercepts, and we'll figure out domain and range as well, but most of today will just be review from stuff you've already known, so it shouldn't take us too long to go through. And then as we move through the unit, we'll look at doing asymptote lines, max and mins, inflection points, all of these things there where derivatives will help us draw a graph. So ultimately your goal is you should be able to graph any sort of function by hand without relying on your graphing calculator. And that's what you're going to need to be able to do to move on to university calculus. So we'll get started today, and like I said, most of it's review, stuff you've already done before, but it's quick. It's good to kind of go through it quickly to refresh yourself. So what we're going to do today, we're just going to look at some examples, and we'll just go through how to algebraically calculate x and y intercepts, and then we'll sketch the graph and figure out our domain and range. So remember, to calculate x and y intercepts, you basically just plug a 0 in. We know that when x is equal to 0, we get our y-intercept. So if we plug a 0 in for x, we get our y-intercept at -6. So we know that our coordinate 0, -6 is on our graph, so let's plot that one. And then we do the same thing for our x value, but make y equal to 0. And then just rearrange and solve that equation. So bring the 6 over, divide by 2, we'll get a coordinate of 3, 0. So when x is 3, we have y equals 0. So there's our two coordinates. Being a straight line, we know that it's just going to go through those 2 points and go on and on forever, something like that. So we need to be able to calculate these things algebraically, and then from the graph and from what we already know about functions, we can do our domain and range. And let's practice doing these in interval notation. So because there's no restrictions and x and y would both be just any real numbers, in interval notation we'd write it as -infinity to +infinity for both. Okay, the next one is a cubic equation. So for polynomials, you spent quite a bit of time in Math 30-1 doing quadratics, 4th degrees, 5th degrees, and kind of remembering what they look like and how to get the x-intercepts and all of that. So a lot of this will be pretty much the same. So let's first again plug 0 in for x. So we'd get 0 for both, so that just gives a 0. So 0, 0 is our y-intercept, and it'll also be an x-intercept in this case. For the y coordinate, or for the x-intercepts, plug 0 in for y. And typically when it's anything beyond a linear, we want to factor it. So if it was a 3rd degree, 4th degree, 5th degree, you might have to do synthetic division or long division. In this case, it's pretty easy. We can just factor out an x, and then we can do a difference of squares. We get +2 and -2 as our two factors. So then we know from those factors our x-intercepts would be at 0 for the x value, -2, and +2. So we can graph those two on there. And we know it's a cubic graph, so we know it's going to kind of go diagonally and look something like that. Okay. For now, we're not going to worry too much about where those max and mins are. We'll get to that in the next couple of days. We'll be able to figure out exactly where those two locations are, and we'll be able to draw these a little bit more accurately at that point. But for today, just get your x and y intercepts like we did, and we can see again our domain and range would be any real number for both. So write them as -infinity to +infinity for both of those. Okay, the next one we got is a square root graph. If you remember back to Math 30-1, a regular square root graph starts at the origin and goes upwards, something like that. So the only thing that we could approach these from a transformation point of view, which we could see that this would be a 1/2 horizontal stretch and translated to the right. But let's do it algebraically again. So let's plug a 0 in for the x value. And that'll give us square root of -4, which we can't do, so that means there is no y-intercept. Okay, right, just because we can't do square root of -4, so that gets rid of that. For the x-intercept, To get rid of the square root, let's square both sides. So that'll give us 0 equals 2x minus 4. Bring the 4 to the other side, divide by 2, and we get 2. So we know, let's get rid of this graph, so we know that our x-intercept is going to be at 2 instead. So we can plug that on the graph, and again it's just going to be still a regular looking square root graph. Being that it's half horizontal stretch, it'll be a little taller than normal. It'll look something like that. And then from there, our domain and range, we can see our domain starts at 2 and goes to infinity, and our range is starting at 0 and going up to infinity as well. Next one is a rational graph. So remember, like a basic y equals 1 over x, we tend to get two curves sort of in opposite quadrants, something like that, with asymptote lines at the x and y axis. We're not going to worry too much about the asymptote lines today. That's going to be our main topic in the next lesson. But we can kind of use what we know from Math 30-1 to figure it out, to get a rough sketch anyway. So let's do it algebraically again. Let's make x 0. So in this case, when x is 0, we would get 3 plus 0 over 3 minus 0, which would give us 3 over 3, which is 1. So we know that our x-intercept is at 0, 1, or sorry, y-intercept. And let's do it algebraically when y is 0. So we'd bring that 3 minus x up to the other side. But because we're timesing by 0, that'll all turn into 0 anyway. So we get 0 equals 3 plus x, and subtract the 3, and we're done. So our x-intercept would be at negative 3, 0. So we can plot that. So we know our curve's going to be between those 2 points. So let's do just a quick refresher from Math 30-1. If you remember, the non-permissible on the bottom gives us our vertical asymptote. So we know that x can't equal 3, so that would be our asymptote line in the y direction. I'll just draw it as a solid red line here. So there's our one asymptote line. And if you remember from horizontal asymptotes, it comes from dividing those coefficients. So in this case, we'd have 1 divided by negative 1, which would give our horizontal asymptote at negative 1. And that should be good enough. We can see now that our curve would go between these 2 points, something like that. And then on the other side, it would be symmetrical. It would end up being something like that. And that's good enough for now. We'll get into the asymptotes a little bit more detail tomorrow. So in this case, our domain and range would be everything except for those asymptote lines. So we'd go from negative infinity to 3, and then go union 3 to infinity. And then the range, same thing, negative infinity to negative 1, and union negative 1 to positive infinity. One of our other functions we spent lots of time in Math 30 was trig. So remember, trig, we should remember our basics of sine graphs and cosine graphs. So in this case, I've got a domain as well. So this is given to us as a certain domain, but we'll worry about that later. Let's just deal with our intercepts again. So if we plug 0 in for x, sine of 0 from the unit circle is 0. So we'd have 3 times 0, which is 0. So again, the origin is one of our coordinates. And if we do our x-intercepts, plug 0 in for y, divide by 3 would still be 0. And again, from the unit circle, we should remember that x will be 0, our sine x will be 0 at 0, pi, 2 pi, and so on. So it'd be every pi apart. So if I was to do the entire graph, we would graph this at every pi location. So it would look something like this, and also in the negative direction. And then we would draw our full graph as a regular sine graph. So the only thing we got to be careful of in this case is our domain is only between 0 and pi. So that means we're not worrying about the negative quadrant, we're not going anything past pi. And if you remember from Trig, the 3 out front, our amplitude will tell us what the range will be. So it's going to go from 0 to 3. So in that section of the graph then, in that section we would just go from 0 up to 3 and back down to pi. And that should be our only section of the graph. If we were to continue it, if that domain wasn't on there, then it would also go down to -3 and so on in each direction. But that's it for this question. So our last topics that we did in Math 30 were logs and exponents. We figured out what those graphs look like. We'll do the same, but today we'll focus on just base e instead of base 2 or base 5 or whatever. So if you remember, for an exponent graph, it typically follows the x-axis, crosses through a y equals 1, and then just increases beyond that. So with this one, the way I've got it sketched, it's probably about a y equals 4 to the x graph. So if I was to draw y equals 2 to the x graph, it would look pretty similar, except it'd be a little bit lower. So if we do a base e is 2.71 roughly, so it would be somewhere in between. It would end up being kind of like that green graph. Okay, so let's look at doing just the base e, and again let's solve these algebraically, and then we'll be able to sketch out a pretty accurate graph. So our same strategy as before, but with logs you have to be a little bit more careful. If we plug a 0 in for x, we get e to the 0, but anything to the 0 is 1. So in this case our y-intercept is at -1. So that's on our graph. Do the same thing but for y, so let's plug a 0 in for y. Bring the 2 to the other side. And now how do we solve for e to the x? Well, we're going to have to convert it to a log. So if you remember in Math 30, if you had something like 4 to the x equals 7, we could rewrite it as log base 4 of 7 equals x. So we'll do the same strategy here, except instead of log base e, we'll write it as a natural log. So you'd write it as ln 2 equals x. And ln 2 as a decimal would be about 0.6 or something like that. So we could plug that roughly on our graph, would look somewhere in there. So we remember that our basic graph was, the asymptote line was right along the x-axis, what we've gone down to, so now it's going to be down at -2, and then our graph would just curve up something like that. And that's it. So we've got our graph drawn, our domain and range. Domain will be any number again, but our range this time is now bigger than -2. So round bracket, -2 to infinity. Okay, the last graph I got is a log graph. So remember again, with log graphs, they typically follow the y-axis, cross through 1, and then curve up through there. So this time our x-intercept is at 1. So this will do the same thing, except it's natural log or base e, so it'll just be a little flatter. It'd end up going a little bit lower than what I just drew. But other than that, everything works the same. So let's again calculate it algebraically and sketch it out, and then we'll be done. So first thing, let's plug a 0 in for x. So we just get ln 5, which is about 1.6 or something like that. I'll just leave it as ln 5. So that would be, let's just estimate it about there on our graph. And let's do the same thing for our x. And again, we're going to have to convert this to an exponent. So let's make it e to the 0 equals x plus 5. E to the 0 is 1. Bring the 5 over would give us -4. So -4, 0 should be our x-intercept. And again, remember, we could think back to transformations. We move this 5 to the left. So now our asymptote line will be at -5. And then our graph will just follow that, go through our 2 points, and carry on like that. So that's it. So we've got our graph drawn, we've got our x-intercepts, our domain in this case will be greater than -5, and our range will be all possible values. And that's it. So we'll just practice calculating our x and y intercepts algebraically, plotting those on the graph, and then just remembering some basic graphing transformation knowledge, and you should be good. So our next lesson will focus more on just asymptote lines and how we can calculate those algebraically, and then we'll move on to derivatives after that.